Let's look at the data in the question. We are given here a point charge Q1 which is minus 5.8 microcoulomb and it is said to be stationary, it is fixed. Where? At origin. There is a second charge Q2 which in magnitude is plus 4.3 microcoulomb and it is said to move from one location to another. We are given the coordinates of initial and final locations as well. With this information, we need to find the work done by the electric force on Q2. And here are the options. Well, how do you find the work done by electric force for such a displacement of the second charge? You have to remember that we are dealing with conservative force here. Electrostatic force happens to be a conservative one. So you can write the work done by electric force in terms of the change in the potential energy associated with the system. We associate a potential energy with the conservative force, right? So work done by conservative force is negative of the change in the potential energy of the system. And potential energy term involves not only the magnitude of the charges, but also the location of the charges. In the sense, it talks about the distance of separation between the charges. And we can use all the data given here and find out the work done by the electric force. All right. Work done by the conservative force, which is electric force, happens to be minus delta U. What is delta U? UF minus UI. Final electric potential energy of the configuration minus initial potential energy of the configuration. And if you simplify this, it simply turns out to be UI minus UF. Now, how do you write U? The electric potential energy of a configuration of two charges Q1 and Q2 separated by a distance R. You write it as U is equal to K Q1 Q2 by R. Be careful. When you are substituting the value of Q1 and Q2, put the sign as well. In that case, what do we need? The work done by electric force. It turns out to be K Q1 Q2 into 1 by Ri minus 1 by Rf. Ri and Rf are the initial and final separation distances between the charges, and that happens to be 0.26 meter and 0.38 meter respectively. Let's substitute. In that case, it happens to be 9 into 10 to the power 9 into Q1. Remember, it is negative. So, minus 5.8 microcoulomb into Q2, which happens to be 4.3 into 10 to the power minus 6. All right. Now, 1 divided by Ri, initial separation distance was 0.26 meter, minus 1 divided by Rf, which happens to be 0.38. Simplify this and you have your answer. The actual answer turns out to be minus 0.272 joule. What's the meaning of this negative sign here? Let's interpret. The work done is negative. Why? It's because there happens to be an attractive electrostatic force between the two charges. And on second charge, the force happens to be in this direction, whereas the displacement of the second charge is in the opposite direction. Exactly why the work done by electric force happens to be negative here. All right. Now let's look at the options. The correct one turns out to be A. Let's look at the data. There are 4 charges given to us: Q1, Q2, Q3 and Q4. They are kept on the vertices of a square of side 1 meter. And with this information, we need to find the electric potential energy of the system of charges. Here are the options. Well, first of all, let's understand what is this electric potential energy all about. Quickly. If you keep 2 charges separated by a very large distance, there is no interaction between them. But if you want to bring them closer to a certain separation distance between them, which happens to be finite, then there has to be work done. That work done is stored in it as electric potential energy. The force involved here is electric force, which is conservative in nature. And in terms of the work done by electric force, we can write the change in the potential energy to be minus of work done by electric force. In that case, delta U, which is UF minus UI, the final minus initial electric potential energy of the system of charges, system of two charges, turns out to be K Q1 Q2 into 1 by RF minus 1 by RI. What are RF and RI here? The final and the initial separation distances between the charges respectively. If we choose for our convenience Ri to be infinity, then this turns out to be 0. And if we choose Rf to be R, in that case, we can write the change in the potential energy to be simply UF, and that turns out to be K Q1 Q2 divided by R. Remember, at separation distance being infinite between the two charges, we defined the potential energy to be 0. That's how we get this expression. So we have an expression for electric potential energy of a system of two charges separated by a distance r. What do we have here? 4 charges. We have to account for each pair. How many terms will you have? If there are n number of charges, obviously it has to be n into n minus 1 by 2. It has to be 4 into 4 minus 1 by 2. 6 terms. Let's write them down. U net will be K into first term. For this pair Q1 and Q2, it will be Q1 Q2 by R12. What is R12? The separation distance between Q1 and Q2. Second term for Q1 and Q3, that divided by R13. Third one, Q1 Q4 by R14. Similarly, between Q2 and Q3, you can write like this. Then for the pair Q2 and Q4, you can write. And finally, the only pair left is Q3 and Q4. Here it is. All you need to do now is substitute the values for the charges along with the sign and simplify. U net in that case turns out to be K, which is 9 into 10 to the power 9 unit, into Q1 Q2. Let's be careful here. This is 1 microcoulomb, this is 2 microcoulomb. So 1 into 2 divided by separation distance is 1 meter. We will take care of the powers later. Plus Q1 Q3, that will be 1 into minus 3 divided by this separation distance, which happens to be √2 meter. All right. Q1 Q4, that is 1 into 4 divided by 1 plus Q2 into Q3. This is 2 into minus 3 divided by 1 plus Q2 into Q4. 2 into 4 divided by √2 plus finally Q3 and Q4. That is minus 3 into 4 divided by 1 into, what do we have here? 10 to the power minus 12 joule. If you simplify this, the final answer turns out to be around minus 7.62 into 10 to the power minus 2 joule. That's your final answer. Allow me to help you in interpreting the data from the question. We have here a case of two charges. First charge Q1, which is 9.1 microcoulomb, is fixed at the origin. It is always at rest. Look at the second charge. It is called Q2, which is minus 0.42 microcoulomb in charge, and its mass is also given to us 3.2 into 10 to the power minus 4 kg. It is initially on the x-axis at a separation distance from Q1 of 0.96 meter. It is released from rest, and obviously, because of the electrostatic force of attraction between them, Q2 moves towards Q1. When the final separation distance becomes 0.24 meter, at that instant, we are supposed to find the speed of the second charge. That's the question. All right. You should have realized by now that we are not considering any external forces in action here doing any work. In that case, as a consequence, we see that the sum total of potential and kinetic energy in the beginning and at the end must be same. It must be conserved. So we can write the sum total of initial potential and kinetic energy to be equal to final sum total of potential and kinetic energies. All right. What is initial electric potential energy? Because that's what we are looking at here. It will be K Q1 Q2 by Ri. Ri is the initial separation distance between the charges, plus Ki, the initial kinetic energy of the particles. Obviously 0, both are at rest. That will be equal to UF, the final electric potential energy of the system. K Q1 Q2 by Rf. What is Rf here? The final separation distance between the two charges, plus the final kinetic energy. The first particle is at rest at any point of time, so it is 0. For the second particle, we can write half m2 v square. What are we supposed to find? V. All right. Let's simplify this. V square turns out to be K Q1 Q2 into 1 by Ri minus 1 by Rf. And let's transfer m2 and 2 to the other side, cross multiply. What do you get? 2 divided by m. What do we need? V, isn't it? So take the square root on both the sides. V turns out to be square root of, let's simplify after substitution, 2 into K value is 9 into 10 to the power 9 units. Q1 is 9.1 into 10 to the power minus 6 coulomb. Q2 is minus 0.42 into 10 to the power minus 6 coulomb. All right. That divided by the mass of the second particle, which is 3.2 into 10 to the power minus 4 kg into finally 1 by Ri minus 1 by Rf. 1 by initial separation distance is 0.96 meter minus 1 by final separation distance is 0.24 meter. And the final answer after simplification turns out to be around 26 meter per second. Verify it. Look at the options now. The correct one is B. Look at this interesting question we have here. We are considering two charges, equal in magnitude, equal in mass as well for the particles, and they are separated by a very large distance in the beginning. So their interaction is 0. One particle is at rest, the other one is given a velocity v in the direction of the other particle. Now from this moment onwards, this configuration reaches a stage where the separation distance becomes minimum and we are supposed to find that minimum separation distance. All right. You should have realized by now that there are no external forces in play here. What does it lead to? Linear momentum conservation for the system. Also, since there are no external forces doing any work here, the sum total of potential and kinetic energies must remain same for the system. Using these two principles, we can set up an equation each, and finally we can solve for minimum separation distance between the charged particles. Let's do that. First, the application of linear momentum conservation. Pi is the initial linear momentum, Pf is the final linear momentum. Initially, one was at rest, the other one was given a speed v in the other particle's direction. So the linear momentum in the beginning was 0 plus mv. Alright, what about the final linear momentum? Which moment are we interested in? The minimum separation distance moment, correct? Visualize what happens here. These two particles are initially separated by a large distance. When the particle which was given a speed v moves towards the other one, separation distance between them decreases, their interaction becomes non-zero, and it becomes significant. The effect is that the particle which was at rest in the beginning will accelerate. The particle which had initially the speed v will decelerate, and it will continue because there are no external forces involved. This will continue, and there will come a moment when both these particles will have the same velocity in the same direction, and that is the moment we are interested in. That is when minimum separation distance happens. What happens after that? Simple. The particle which was at rest in the beginning, you remember, right? That one will continue with increased velocity, and the one which was given an initial speed v in the beginning will continue to decelerate, and its speed will reduce further. So as an effect, the separation distance again increases. So what's the consequence? Separation distance in the beginning was very large, becomes minimum, and increases again. All right. Now, final linear momentum at the instant of minimum separation distance happens to be mu plus mu. Why? Simple. Since both of them have the same velocity in same direction, I have chosen to call that velocity as u. In that case, u turns out to be v by 2. Let's keep it aside. Now, look at the conservation of energy. The sum total of potential and kinetic energy in the beginning must be equal to the sum total of potential plus kinetic energy at the end. Initial and final must be same. So, ui, in the beginning, the electrical potential energy of the system was 0 because they are separated by very large distance. 0 it is. Plus half into mv square. That's the kinetic energy of one charged particle which was moving. Finally, at that moment of minimum separation distance, R minimum, the potential energy happens to be K Q1 Q2 by R minimum. Plus, what about the kinetic energy? Both are moving with the same speed u. So it will be put together half into 2m into u square. What is u? V by 2. So v square by 4. Simplifying this, we can find an expression for R minimum because that's what we want. Let's do that. You get K Q1 Q2 by R minimum to be half mv square minus mv square by 4. What does that give you? mv square by 4. All right. In that case, R minimum turns out to be 4k. Let's substitute the value of k. It is 1 by 4 pi epsilon naught. Then you have Q1, Q2, and you have mv square. You can cancel 4 in the numerator and the denominator. Exactly why your R minimum turns out to be Q1, Q2 divided by pi epsilon naught mv square. But in this case, Q1 and Q2 are simply Q each. Exactly why this will be Q square by pi epsilon naught mv square. That's the final answer. Let me help you with the data of the question. We are considering a uniformly charged ring here of radius capital R, and the net charge on the ring happens to be capital Q. At the center of the ring is a particle of mass small m and charge Q naught. It is said that a negligible amount of force is applied on the particle along the axis of the ring, displacing it slightly. What do you mean by negligible force? By applying negligible force, you may displace it, but you may not give it a significant velocity. Now, with this information, we are supposed to find the speed of the particle when it reaches a large distance. What do you mean by that? X, the separation distance between the center of the ring and the charged particle later, will be so huge that it will be much greater than capital R, the radius of the ring. All right. Consider the initial configuration. The charged particle is at the center of the ring. Here it is. Do you realize that the net electric force acting on that charged particle happens to be 0 in this case? No matter what the charge nature is for the particle, even if it is negative charge on that particle, the net electric force acting on it is 0. Imagine for a moment that it has negative charge on it. Q naught was negative. Imagine. If this is x-axis that we choose, and we choose to apply a negligible force to displace that particle slightly along x-axis such that it comes here. What's the effect? Do you see that there is electrostatic force of attraction between capital Q and Q naught in that case, which happens to be in this direction. It's like a restoring force trying to bring back that charge Q naught to the center of the ring again. However, the charge we are considering here happens to be positive in nature. Exactly why? When it is slightly displaced along the x-axis, let's say to this position, the effect is that there is electrostatic force of repulsion acting on Q naught in this direction along positive x-axis. And theoretically, it should continue to move along the straight line all the way till infinity. Now, if this is how the motion of the charged particle happens, how can we find the speed of the charged particle when it reaches a very large distance of separation? Simple. I hope you have realized by now that there are no external forces doing any work here. Also, the only force we are considering here is electrostatic and conservative in nature. The consequence is that the net energy, I'm talking about the sum total of potential and kinetic energy, in the beginning and at the end, they are the same. It's conserved. With the application of this principle, we can solve for the speed of the charged particle when it reaches a very large distance of separation. Let's do that. In the beginning, the electric potential energy for the configuration happens to be K, Q, Q naught by capital R. Because effective separation distance between capital Q and Q naught happens to be capital R. That plus, what's the kinetic energy of the system in the beginning? 0. That's equal to, when the two charges are separated by a very large distance, electric potential energy happens to be 0. So UF is 0 plus KF, the final kinetic energy. Only the charged particle is in motion. Let's say with a speed v, it will be half mv square. Let's solve for v now. You will get v square to be 2k q q naught by m capital R. Take the square root and you have your answer. And it turns out to be square root of 2k q q naught by mr. Now look at the options. The correct choice is D.